Hello, class. I hope you had a wonderful Thanksgiving. Here we are in week 6 of Introduction to Business Statistics, or something like that, right? Stats class. Okay, I want to talk about a little bit more about our CT assignment for this week. One thing that a couple of you have picked up on, and I don't know how many of you have picked up on this, is that this class used to be taught in a different way. And if you've looked at those computer examples in our text, you see that there's this thing called Data Analysis Plus. And it was also offered to you if you bought the textbook. It's an add-in besides the one that we already are using for Excel. It's a second add-in. However, the new class, the way it's taught now, starting just this semester, is that we don't need that second add-in. Everything I show you, we can do just within Excel. Now, if you're using that add-in, which I believe it's still available, you know, you're kind of on your own. Don't ask me questions about it. Well, I shouldn't say that. No one's asked me questions. I would answer questions, but, you know, the way that I'm teaching the class is with Excel alone. Okay. No big deal. Let's move on. Let's talk about confidence intervals. First of all, we are going to calculate confidence intervals. And what is a confidence interval? Well, I'm going to read from my textbook on page 274. And if you have your book, please open it up to page 274 because we're going to look at a diagram, a figure on that page as well. A confidence interval is an interval estimate for which there is a specified degree of certainty that the actual value of the population parameter will fall within the interval. Well, what does that gobbledygook mean? It means this. We're going to take a sample from a population, and we're going to calculate, let's say a mean value from that population. Example I'm going to show you has to do with shoe size. So let's say we calculate a mean shoe size. What we want to do now is calculate what's called a confidence interval. How confident are we that the true value of the mean, that would be the population mean and not the sample mean, how confident are we that the population mean is included in an interval that we calculate? Well, it turns out it's fairly simple to create this confidence interval. We need the mean, we need n, the number of sample points, and we need either the sample or the population standard deviation. And with that much information, we can calculate this confidence interval. Let's see. So on page 274, if you look at that figure in the top, at the very top it shows a normal distribution, and it shows that there's some parameter or some mean of some value of whatever this parameter is, and its mean value is 20. That's the estimate of the population mean. It's only the sample mean. No, I take it back. This is the population mean. They're saying for this example, okay, let's say we knew everything about the population. Everything. We knew what the value of every single member in the population was. Well, then we could calculate the population mean. And for this example, it's 20. Then they said, okay, 1, 2, 3, 4, 5, 6, 7. They're going to pull 7 different samples and calculate these things we call confidence intervals. And those are the 7 things shown in the lower part. For example, the first sample, they calculated a mean, they call it X bar 1 of 22. And the confidence interval, which we don't know how to calculate yet, but we're about to learn how, ranges from 15 to 29. Did they capture the sample mean within their confidence interval? Yes, they did. That's a good thing. But it doesn't always happen. We always associate some degree of confidence with whether or not we believe the actual mean, that's the population mean, falls within our confidence interval? Well, let's see. They did a pretty good job, except for that third one, didn't they? They happened to pull values, a sample, that resulted in a mean of 30.5. Then when they calculated their confidence interval, it ranged from 23.5 up to 37.5. Does the real mean of 20 fall within there? No, it does not. That's not good, but that happens. That's statistic. That's statistics. So let's see, confidence intervals. We usually choose the 90% or the 95% or the 99% level. Think about this. For a confidence interval, as I increase the confidence level, that is how confident I am that the true value of the population parameter falls within the confidence interval, as I increase the confidence level, going from, say, 95 to 99%, will that confidence interval get larger or smaller? I believe we have a discussion question that tackles that. And, well, you will see, you will find out before long the answer to that question and other exciting statistics questions. Okay, so confidence intervals. We're going to calculate them. Let's flip now again over to page 276, one turn of the page, and I'm looking at that figure 9.2 because there's some good stuff here. This chart shows you the three equations that we will use in our work to calculate confidence intervals. Now, there are two types of confidence intervals that we look at in our class. They are confidence intervals of the population mean and also confidence intervals of the population proportion. The two left-hand columns of this figure are for equations for calculating a confidence interval for the population mean, and the one on the right is for calculating some proportion. And what is that proportion all about? Well, in the example that we're going to use, I'm going to show you on Excel, I'm going to calculate the confidence interval for shoes of size 10 in our example. So I'm going to be so and so confident that that my proportion of shoes, I'm going to, how do I say this? I am going to create a confidence interval about my point estimate of the proportion of size 10 shoes. We'll come back to that one. But it's a simple proportion. It's a probability. We've done these. We know about those. We know how to calculate those, and you will see it's pretty simple how to do it. Okay, back to the figure. If I wanted to calculate the confidence interval of a population mean, I come down that left-hand side, and you can see there's two paths to go. I can go down the left-hand side or down the center of this diagram. If I knew what sigma was, and what is sigma? Sigma is the sample population standard deviation. Sigma, say that again, Craig, slow down. Sigma is the population standard deviation. It is the true standard deviation. If sigma was known, well, then we have an equation for calculating our confidence interval. When would this be known? Standard deviation. Okay, let's see. If you pull a sample of values from the population, you can calculate a mean and you can calculate a sample standard deviation. But when are you going to have a population standard deviation? Well, one example I can think of is, let's say you're a manufacturer and you've got this big ugly machine and you've been using it for 20 years. And you know, after taking trials once a week for 20 years, that this thing, week in, week out, gives you a standard deviation on part size that it creates, a standard deviation of 0.01 inches. That's the standard deviation of how big of part size this thing makes. So in that case, you could say sigma, the population standard deviation, is known. And you could use the equation that's in the third box down the left side. They say z interval with limits. And what is the confidence interval? Well, it's x bar plus or minus the z statistic times the population standard deviation divided by the square root of n. We'll talk a little bit more about these z's and sigma in just a minute, but first let's look at the next equation. This is the much more common equation, and this is the one that we will be using in our work. In this case, we're not going to know what the population standard deviation is. We're going to have to use a sample standard deviation. Yes, we have values we've drawn from the population, and we're going to calculate this parameter, this sample standard deviation. Okay, in this case, we use what's called a t-interval, and the confidence interval that we will calculate will be equal to x bar, which is the mean, plus or minus the t-statistic times sample standard deviation divided by the square root of n, the sample size. Finally, if we are looking for a confidence interval on a proportion, we will use the third equation in that figure, the one on the far right. And let's see, if I'm not mistaken, I put examples of these in the videos that I sent you, or I'm sorry, will send you shortly, and you will see how they're used. Okay, let's look at an example in Excel. I want to show you, you don't really need Excel to do this problem, truthfully. However, we have 150 data points. Excel will snap those up in means and standard deviations much quicker than you can. So let's look at what I have here. I have listed shoe sizes of how many people? I forget. I think it's 20, 27, 28, something like that. We're going to calculate that. And they range from 5, up to 12 or something like that. Of course, I just made these numbers up. But I'm looking at shoe sizes. Must be both men and women, or men, women, and children. I don't know what it is. Don't really care. Let's look at how we calculate confidence intervals. In this case, I want to construct a 95% confidence interval for shoe size. What do I do? Well, first of all, I need what's called a point estimate of the mean. What is our best estimate of the mean value of our data? Well, the best we can do is get the sample mean. So I am going to do that. I'm going to use Excel's average function. And it's real simple. I'm going to go like that. And boom. The average shoe size is 9.11. I don't care that there's a fractional part on shoe size. I'm just going to accept that. What is the standard deviation? Now, we've used that descriptive statistics function before in our Excel add-in, but, Excel also has a real simple equation for doing this. If I can remember it, STDEV, there it is. And once again, I need to grab my data and say boom, ba bum. So the average shoe size is 9.11 with a standard deviation of 2.21. How many values do I have? I'll use the count function for that. I will first learn to spell and then use the count function. In my sample, I have 27 values. Now, the equation that we're going to use, let me find it for you. Again, we were looking at our figure 9.2 and we said it's the t-interval one. We're going to have a population mean. We don't know what the population mean is. That's what we're creating a confidence interval for. Do we know the sample I'm sorry, do we know the population standard deviation? No, we do not. We're going to use our estimate of it, which we just calculated as 2.21. And so I need the equation, which tells me is section 9.5. So I'm going to flip over to section 9.5. I'm in section 9.5. No, I'm not. There it is, 9.5. The student's t distribution. Good stuff. In particular, I'm looking at the example on page 285. This is a very good example to look at. Okay, when we need to calculate a confidence interval, we need to choose an appropriate t-statistic. And I leave it to you to learn how to do that. The book was pretty specific. But for my example, and it's the very back inside cover of the book, we need to find the t-statistic. Hold on a second. Let me look here. Sorry about that. I panicked for a second. When we're looking for the t-statistic, we need two parameters, and I've listed them here. It's the confidence level, and our confidence level for the problem I'm doing is 95%. I believe yours is the same. And the degrees of freedom, which are simply equal to n minus 1, is 26. So a t distribution, the tables that you find are one-tailed, and so you have to take first you take the 95% confidence level, you take 1 minus the 0.95 to get 0.05, and then you take half of that. So the alpha level I need is 0.025, and the degrees of freedom is n minus 1, or 27 minus 1 equals 26. It's not the back cover of the inside back cover of the book. That's the Z, the normal distribution, but one page in is the t distribution. And if you find the row with degrees of freedom equals 26, and you look at the alpha column of 0.025, you will find that the t-statistic I need is 2.056. 2.056, and I'll write that one down. Okay, and now I'm ready to calculate my lower confidence limit and my upper confidence limit. How do we do that? Well, it's pretty simple. Let's see, I'm jumping back. Should have stuck my pencil on that page. Chapter 9. Oh, that's chapter 10. Here we go, I'm close. There we go. Again, I go back to our chart on page 276, and I'm going to use that equation in the very center of the chart. I want x bar plus or minus t times the standard deviation divided by the square root of n. Well, we have everything there. We have our t-stat, we have n, we have standard deviation, and our mean. So it's simply a matter of creating an equation. And I'm going to hide that one from you this week. I'm not going to show you how to do it. It's real simple. You just plug in the values into that equation. Back in a jiff. I have calculated my upper and lower confidence interval limits. Basically, I've created my confidence interval. It runs from 8.24 up to 9.98. And I'm just going to repeat that here. Oftentimes we write confidence intervals. It looks like an ordered pair, but this is how we sometimes do it. So, what's our interpretation here? This is the important part. Our interpretation is thus: we are 95% confident that the true value of the population mean falls between 8.24 and 9.98. It's that simple. Is there a chance that it does not fall in that range? Well, you bet there is. We're only 95% confident that it falls in that range. It might not, but we're pretty sure that it does. How could this sort of information be used in planning? Let's see. What are you guys going to be calculating confidence intervals of? Attitudes toward the malls. Well, I guess, I'm going to leave that to you. How does the manager who's looking at those values interpret that confidence interval? We'll leave that for you to write about. Okay, so again, the equation that created my 8.24 and my 9.98 was fairly simple. It's that one in the very center of figure 9.2. That's the one we need to know. I won't say more than that. Okay, you were also asked, what is the maximum possible error that your confidence interval gives? Well, keep in mind that the mean, 9.11, sits halfway between 8.24 and 9.98. So the maximum error is simply the distance from the mean to one end or the other. Or I suppose there's another way we could do that. We could calculate it by taking one end of the confidence interval, subtracting the other. Oopsie. Subtracting the other, wrap those in parens, and divide it in half, which is the same thing as the distance from, since the mean is right in the middle, it's the same thing as the distance from the mean to one end of the confidence interval or the other. There's the maximum error. The maximum error we can possibly make using this confidence interval is 0.87. Okay, let's move on. It's a very similar process for calculating a population, the confidence interval about a proportion. So first of all, the question I'm asking is, I want a confidence interval on the proportion that says shoes are size 10. Well, as you look through this data, you can see there's a few 10s, but they're not all 10s. So what we need to do is calculate our point estimate of the proportion of size 10. We're simply going to calculate that proportion, or we called it probability, that a 10 comes up in the sample. So first of all, count of size 10. How many 10s are there? Do I need that information? I must. At least I think I do. Well, we'll do it. Count. Let's see. I need... No, I need count if I'm doing this. I need a range. Yeah. First I give the range. Sorry, Excel. And then I give the value that I want it to find. And so Excel looked, and there are 7 size 10s out there. All right, Excel's yelling at me. Let's see, A6 to 31. Did I get everybody? Oh, I missed one. Thank you, Excel. Let's try that again. It's A6 to 32. Sometimes those errors are meaningful. There's 8 of them. The last one was a 10. All right, and how many total did we have? Well, we knew there was 27, but I'm going to use my equation one more time and say boom, daddy, boom. We've got 27 values. And now I need my proportion of size 10. I need to estimate it, my point estimate of the proportion we're looking at. And of course, it's real simple. We simply take the count of size 10s divided by the 27. And we can say it's that divided by that. And 30% of the values are size 10. Well, that's our sample proportion. How confident are we that the real value, the population proportion, is going to fall within there? You know, I sampled 27 people's shoe size, but I'm really interested in the shoe size of everybody in the state of Wisconsin. And so this is simply a small sample. So how confident am I that this 30% proportion includes the actual population proportion of people's in Wisconsin shoe size? Well, that's what we're going to calculate. Okay, I need a standard deviation of the sample. Well, we've done that before. I'll just do it again. Equals STDEV parenthesis. Grab your data range, close the parenthesis. 2.2. How come I got a different value? Oh, I didn't. Sorry. That's my t-stat. Looks kind of similar, doesn't it? My t-stat, let's see. I've got the same parameters. My confidence level is 95%, which 1 minus 95% is 0.05, and divide that in half because the t-table only looks at one tail. So we have 0.025. Degrees of freedom are n minus 1, which is 27 minus 1 is 26. And once again, we'll get the same value as we had before, 2.056. Confidence intervals. Now let's go back to page 276. For calculating proportions, our equation looks a little different. It's P, which is our proportion estimate. In this case, it's the 0.3, times the Z statistic, times the square root of proportion, times 1 minus proportion, divided by N. Okay. Well, let's see. The Z statistic is similar to the N statistic. It's a little bit more liberal versus the T statistic is more conservative. And we know from either using the table in the back of our textbook, well, it's kind of tough to look at. No, it's not so tough. Let's see. How do we do it? We have a Z value, 1.96. You have to use it kind of backwards, and I'll leave that for you to figure out. 1.96, yeah, 0.9750. But on page 277, we have confidence level Z statistics, or Z statistics for the most common confidence levels. You can see that for the 95% confidence level, we use 1.96. So there's a value we need. Again, back to our equation on 276 on the far right of the figure, we need P, which is our proportion, 0.3, plus or minus Z, which is our 1.96, times all that stuff underneath the radical, the square root stuff. I'm going to put that down right now, right back with you. I've made the calculations that you will need to make. And I calculated both the lower and upper confidence limits, creating my confidence interval. I'm just going to repeat that data again here, like I did before. Let's see, 0.124, comma, 0.469. And if you want to write them in your paper that way, that's a good way to write confidence interval. What does it mean? What's the interpretation? Once again, I have an estimate of the proportion of size 10 people, and it's 0.3. About 30% of the people in my in the sample I drew have size 10 feet. Question is that the true population proportion? We don't know. However, based on our sample size, our standard deviation, and our T statistic, we can calculate that we are 95% confident that the true value of the population proportion falls between 0.124 and 0.469. or somewhere between 12.4% and 46.9%. All right, let's see, maximum error. Again, we can simply subtract these two values, the endpoints of our confidence limits, and divide by 2. That's not going to work, is it? No, need a pair of parens around those guys. Otherwise, we're dividing G11 by 2 and not the difference. All right, there's the estimate of the maximum error in my confidence interval. I spoke earlier about what the effect would be of, well, actually, I don't even remember which parameter we looked at, but let's see. Let's look at it again. Let's look at our population proportion. If our standard deviation was greater than 2.21, how would that affect our confidence interval? Would it squeeze it closer together or push them out? Well, let's think. Standard deviation has to do with variability. Okay, I got an answer. Do you? How about sample size? Usually as we increase sample size, we get better statistics, don't we? Well, let's see. If I increase sample size and statistics get better, is my confidence interval going to get wider or more narrow? You might want to take a look and see where n appears in the calculations that we did to derive those two numbers. There's your answer. What's the other parameter? Well, it's our t-statistic. How does it change? Well, it changes with confidence level and with degrees of freedom. Degrees of freedom are based on n, so there's another factor that changes with sample size. But more importantly, it changes with confidence level, and I guess that's the one I talked about earlier. Let's say I'll go down to this is a 95% confidence interval. If I went up to a 99% confidence interval, this value would change. And because of that, and because this t-stat is used in our calculation of our confidence interval, our confidence interval is either going to get wider or more narrow. Now let's see, if I'm going to be more and more confident that the true value is in here, do you suppose these are going to get larger? I mean, more spread apart, or are they going to get narrower together? Looking at it the opposite way, let's say I'm going to look at with much less confidence. Not the 95% level, but maybe the 70% level. Okay, I'm only 70% confident that the population parameter falls in my range. In doing that, we're going to get a different t-statistic. 70 would be half of that with 0.3, or the 0.15 alpha level. And if we're much less confident, should this confidence interval spread out more or get narrower? I'll have a discussion post about those things. At least I think I do, or I should create one because it's a good topic. Okay, folks, that's a long video, 33 minutes. I don't know what YouTube's going to say about that, but I'm going to find out. I hope, once again, I hope this has helped you, and please let me know if I've made any gross errors or if you have any questions. See you on the boards.